Imagine for a moment a master woodworker, right? Meticulously carving, aiming for that perfect shape.
Yeah, or like an artisan with clay just striving for symmetry.
Exactly.
Yeah.
There's this real satisfaction in seeing something crafted just right. Precision. Yeah.
Definitely. But then imagine throwing intense localized heat into the mix, like with welding.
Right. Suddenly those perfectly lined up pieces they can twist, warp.
Yeah.
Go completely out of whack in ways you really didn't intend.
It's like this invisible dance of forces happening every time you join metal with heat. Welding, just by its nature, involves that intense local heating and then rapid cooling.
Yeah.
And that whole process creates these uneven stresses inside the material. It expands, then contracts, and bam, you get a permanent change in shape.
Distortion. That's the word, isn't it? The sort of silent enemy of precision fabrication.
Exactly. It really is. And, while clever design choices and maybe some post-weld treatments, they're definitely important for managing those stresses or fixing warp later.
Sure, they have their place.
Today, we're really grabbing the magnifying glass and looking at the hands-on stuff.
Okay.
We're diving deep into the actual techniques, the nitty-gritty. What skilled fabricators do during assembly and welding to stop those shifts happening in the first place?
To keep things straight.
Precisely where they need to be, yeah.
So our mission for this deep dive, then, is to unpack these ingenious assembly methods and the specific welding procedures that cut down distortion right from the get-go.
That's the plan. You're going to get a real practical shortcut and understanding of the how-to for keeping structures straight, strong, and, perfectly shaped, even with all that heat.
Making sure the final thing isn't just strong, but also dimensionally spot on, ready for whatever comes next.
Fit for purpose, right off the jig.
Okay, let's unpack this. It sounds like a lot of the battle against distortion is actually fought, and maybe won or lost, before the main welding even really kicks off.
Oh, absolutely. Or right as you're putting the pieces together, it's all about setting that stage correctly. And what's really fascinating is how sometimes quite simple choices at the start, these initial assembly decisions, are just so critical.
Simple but critical.
Yeah, they're all about managing those basic forces. The thermal expansion, the contraction that just happen during welding.
Get those early steps wrong, and you're fighting physics from the first spark.
You got it. It's an uphill battle from then on.
Okay, so where do we start? What's the first line of defense in these pre-weld strategies?
Right. Let's begin with tack welding. Now, you might look at these and think, oh, they're just little temporary stitches, holding things loosely.
That's what they look like. But I get the feeling there's more to it. More strategic thinking.
You're spot on. Tack welds are foundational. They're perfect for setting and, really importantly, maintaining that precise joint gap, that little space between the parts.
Okay, holding the gap.
But it's more than just holding.
Yeah.
They actively fight back against the transverse shrinkage. That's the material trying to pull itself inwards, across the weld as it cools down.
Ah, okay. So the tacks are like little anchors holding the line against that pull.
Exactly. And how well they work? Well, that depends on a few things. The number of tacks you use, how long they are, and the distance between them.
Not just random placement, then.
Definitely not. It's not one size fits all. For instance, too few tacks, or maybe they're too short. You risk the joint closing up as you weld.
Squeezing together.
Yeah, or even overlapping, especially with processes like MMA, manual metal arc, or MIG-MAG welding. Those tend to have a fairly large molten pool pushing things around.
Okay, so not enough tacks means parts might just pinch together. What about the opposite?
Well, here's a twist. With something like submerged arc welding, which uses a really deep, big weld pool.
Right.
If you haven't tacked it properly, the joint might actually open up as you go along.
Oh, wow. So it pulls apart instead.
Can do, yeah. Presents
Right.
a whole different challenge. It really shows you need to understand the forces involved with whatever process you're using.
It's clearly not just about slapping on a few tacks randomly. So the sequence you apply them in must matter too, especially on, say, a really long seam.
Absolutely critical. The sequence is just as important as the tacks themselves. For a long joint, sure, you could just tack straight through end to end.
All right.
But if you do that, you'll almost certainly need extra help, like clamps or wedges along the way, to fight that shrinkage and keep the gap right.
Right. Makes sense.
A more common way, often better for long welds where distortion can really build up, is starting at one end and then using a backstepping technique for the rest of the tacks.
Backstepping, even just for the tack, sounds like you're already fighting distortion before the main event.
That's exactly it. You're preempting it. Or another way, you could start tacking right in the middle of the joint
Okay.
and then complete the tacking by backstepping outwards from the center.
Huh, interesting.
And here's a neat trick, shows the kind of precision involved.
Hmm.
You can use directional tacking sometimes to deliberately close a gap that's maybe opened up a bit too wide.
Pulling it back together with just tacks.
Gently, yeah. It's quite precise work, even for what seems like a temporary hold.
Incredible. And I guess if those tacks are actually going to become part of the main weld, they need the same level of care, right? Same standards.
Oh, absolutely vital. If a tack is going to be fused into the final weld, it must follow the approved welding procedures.
Qualified welders, proper materials.
The whole 9 yards. Qualified welders, maybe preheat depending on the material, same approved consumables as the main weld, everything.
And taking them out. If they aren't part of the final weld.
Even that needs care. You've got to remove them properly to avoid leaving little defects or stress points on the surface. A tiny nick from a badly removed tack can easily turn into a serious crack during the main welding.
Wow, so much thought in those tiny welds. Okay, speaking of clever tricks, this next one sounds almost like magic. Welding 2 identical parts back to back. How on earth does that help? Seems like you just double the problem.
Huh. It does sound counterintuitive, doesn't it? But it's all about using symmetry to your advantage, balancing the forces.
Okay.
Think about the bigger picture. By tacking or clamping 2 identical components firmly together, back to back, you essentially balance the welding stresses around the neutral axis of the combined pair.
The neutral axis.
Yeah.
Like the center line.
Exactly. That invisible pivot point where opposing forces can cancel out.
So, wait. You weld them as a pair, and they both distort.
Yeah.
But in opposite ways.
Precisely. Because they're identical and mirrored, they each try to distort, say, curve inwards, but because they're joined.
They pull against each other and stay straight overall.
That's the idea. While they're still joined as one unit, their individual distortions effectively counteract each other. It keeps the whole assembly much more stable dimensionally.
That is clever, but then you have to separate them.
Right, and that's the tricky part. You need to manage the stresses locked inside. Ideally, the recommendation is often to stress relieve the entire assembly before you separate the parts.
So, weld them, heat treat the whole thing to relax it.
A thermal stress relief.
And then cut them apart.
Exactly. That helps ensure they stay straight once they're individual components again.
Is there another way?
There is. Sometimes fabricators insert wedges between the components before they separate them.
Wedges? Why?
The idea is that these wedges introduce a controlled pre-stress. So when you remove the wedges after separation, the parts are engineered to spring back into the correct straight shape.
Wow, so you're using the expected distortion to actually correct itself.
In a way, yes. It's leveraging the material's behavior very precisely.
Okay, that's back to back.
Yeah.
What about just reinforcing things? If something wants to bow, can you just add support? Seems simple.
It is simple in concept, but very effective, yes. Longitudinal shrinkage, especially in butt welds on thinner plates, often causes bowing along the length.
Right.
So to counteract that, you use longitudinal stiffeners, usually flat bars, maybe angle sections.
And you just weld them alongside the seam?
Pretty much. Welded along each side, they act like braces, providing resistance against that bowing tendency.
Placement matters, I assume.
Oh, definitely. Location is key. If you're welding from one side, any stiffeners on the reverse side need to be positioned far enough away so they don't physically get in the way of the welding torch or arc. Need clear access.
Got it. Okay, so we've set the stage really well with these clever assembly tricks, but now the main event, the actual welding. Does how you weld the process, the technique, make a big difference too?
Oh, it's hugely important. You know, often the choice of welding procedure is driven by productivity, maybe cost, overall quality needs.
Sure. The practicalities?
But the specific choice of process, the technique the welder uses, and the sequence they follow, all of that can significantly sway how much distortion you end up with. It's another layer of control.
Are there some general rules then? For picking a process specifically to keep things straight, my instinct says faster is better, get the heat in and out quick.
Your instinct is pretty good, actually, especially for controlling angular distortion, that bending at the joint itself. For preventing angular distortion, 2 key rules generally apply. First, deposit that weld metal as quickly as you possibly can.
Right. Speed?
And second, use the fewest number of weld runs possible to fill the joint. Less heating and cooling cycles.
Faster deposition, fewer runs. Sounds straightforward. But
I feel like there's a catch, a trade-off.
you've nailed it. There's a classic engineering trade-off right there. Following those rules, fast deposition, few runs, is great for reducing angular distortion,
Ugh.
but it can actually increase the longitudinal shrinkage, the pulling along the length of the weld.
Ah, so you might fix the bending at the joint, but end up with more bowing along the joint?
Exactly. You could solve one problem, make another one worse. So you really need to know which type of distortion is the bigger issue for your specific part.
Like for a long beam, bowing might be the main headache.
Precisely. Whereas for a short, complex joint, maybe angular accuracy is paramount. It depends on the application. Okay, that's a critical point. So which processes usually come out on top if speed and efficiency are the goal for minimizing that angular distortion?
Well, generally speaking, MIG-MAG welding, because it has a high deposition rate and you can move quickly,
Right.
that's often preferred over something like manual metal arc, MMA, stip welding.
Because MMA is slower, stop-start.
Yeah, you're changing electrodes, interrupting the heat flow. It's just inherently a slower process.
And gas welding, like oxyacetylene,
Gas welding typically produces more angular distortion than the arc processes.
more. Why is that?
It's mainly down to the heating. It's slower and the heat source is more diffuse, spread out over a bigger area for longer.
So the metal has more time to soak up heat and, well, move around.
Pretty much. More time for expansion and then contraction, leading to more bending.
What about automating it? Mechanized welding, does that help?
Oh, massively. Mechanized techniques often combine very high deposition rates with high travel speeds.
Best of both worlds.
In many ways, yes. Plus, the heat input and speed are incredibly consistent because it's machine controlled.
And consistency helps how?
It means the distortion you do get tends to be very predictable. And if it's predictable...
You can plan for it, like pre-bending the parts the other way.
Exactly. Techniques like presetting or pre-cambering become much, much more effective because you know exactly how much the part is going to move. You can dial in the compensation really accurately.
Okay, so process choice matters a lot.
Yeah.
What about the finer points? The specific way the welder actually lays down the bead. Technique. Does that play a role?
Yes, absolutely. There are some definite rules of thumb here, too. First, and this is a big one, always keep the weld, especially fillet welds, to the minimum specified size.
Minimum size. Not bigger is better.
Definitely not here. This is a real aha moment for a lot of people. Overwelding, making the weld bigger than the design calls for, dramatically increases shrinkage and distortion.
Why? Just more heat.
More heat, yes, and crucially, more weld metal contracting as it cools. And here's the ticker. It often doesn't actually increase the joint strength beyond what's needed.
So you're adding more stress and distortion for literally no gain in strength.
Precisely. You're just creating problems. So stick to the specified size.
Good tip. What else on technique?
Second, use balanced welding. Remember that neutral axis?
Yeah, balancing forces.
So for something like a double-sided fillet joint, the ideal scenario is two welders working at the same time, one on each side.
Mirror images.
Exactly. Perfectly balances the heat input. The opposing distortions cancel each other out beautifully.
What if you only have one welder? Or for a butt joint?
For butt joints, the order you lay the runs in becomes critical. You might put a run on one side, which causes some angular distortion.
It bends one way.
Right.
Yeah.
Then you put the next run on the other side specifically to pull it back straight. It's corrective.
Ah, okay. Using subsequent runs to fix earlier movement.
Exactly. And the third point on technique. Keep the time between runs as short as possible.
Why? Less cooling time.
Right. The less time the material has to fully cool down and contract between each pass, the less total distortion tends to build up. Keep it warm.
So weld size, balance, and minimizing time between runs.
Got it.
And you mentioned angular distortion depends on runs.
Yeah, it's affected by the joint shape, the weld size, and definitely the number of runs. Generally, for the same size weld, using more runs tends to create more angular distortion because of those repeated heat cool cycles.
Fewer, faster runs wins again for angular if you can manage the longitudinal shrinkage.
That's the balance, yes.
Okay, finally, the actual path the welder takes, the sequence. That feels intuitive, like drawing a line slowly versus quickly, managing the heat trail.
It is intuitive, and it's incredibly important. It makes a huge difference. For instance, on a long weld, just starting at one end and welding continuously all the way to the other.
Bad idea.
Almost always leads to severe distortion piling up at the far end. Not recommended.
So what should you do?
Generally, the welding direction should be towards a free end of the joint, if possible, somewhere the material has room to move and relieve stress a bit.
Okay. And short runs, you mentioned those.
Yes, breaking up a long weld into shorter segments is very effective for controlling distortion. Instead of one long, continuous heat source, you have smaller, manageable ones.
Cool. And there are specific named techniques for doing this, right? Backstep and skip welding.
Exactly. Two excellent ways to manage heat strategically.
Tell me about backstep first. How does that work?
Okay, backstep welding. Imagine you need to weld a seam from left to right overall.
Right.
With backstepping, you deposit short individual weld lengths, maybe a few inches long, but you lay each one down moving right to left.
Opposite to the overall drape.
Exactly. So you weld a short bit right to left, then you lift off, move further left along the joint, and lay the next short segment right to left again.
So you're kind of stepping backwards as you move forwards.
That's a perfect way to put it. It stops heat building up excessively in one direction and prevents that cumulative stress.
Clever. Okay. And skip welding, how is that different?
Skip welding is more like stitching with gaps. You lay down short weld lengths, again, maybe a few inches, but you do it in a planned sequence, leaving spaces between them. So you weld a bit, skip an equal length, weld the next bit, skip again, and so on, all along the seam.
And the direction you weld each little bit.
The direction for each short length is usually the same, often just following the overall progression, but it doesn't have to be opposite, like in backstepping.
So you make a dashed line of welds first.
Pretty much. Then once those initial welds have cooled a bit, you come back and fill in the gaps you skipped.
Why is that helpful?
It distributes the heat much more evenly along the entire joint length right from the start, prevents heat concentration. Often, the length of the weld segment and the skip length are about the same as the run-out length of one electrode.
How much you get from one stick?
Exactly. It makes it practical for manual welding. Both backstep and skip are really powerful ways to manage heat input and stop distortion getting out of control on long seams.
That really is an impressive toolkit of, well, clever fabrication tricks. Okay, to wrap this section up for everyone listening, what are the absolute top takeaways? The must-remembers for preventing distortion using these hands-on techniques?
Okay, the key things to keep in mind when you're thinking about fabrication techniques for distortion control are, first, use those tack welds strategically. They're not just temporary, they set the gap and resist that initial shrinkage.
Right, tacks are crucial.
Second, think about symmetry. Welding identical parts back to back lets them balance out stresses around that neutral axis. Very effective.
The balancing act, got it.
Third, use longitudinal stiffeners, especially on thinner plates with butt welds, to fight that bowing tendency along the length.
Reinforce against the bow.
Fourth, when you're choosing your welding procedure, process, technique, prioritize getting the weld metal down quickly and efficiently.
Speed helps angular distortion.
Often means choosing MIG-MEG over MMA or gas, maybe mechanized over manual if possible. But remember that trade-off with longitudinal shrinkage.
Right, the trade-off is key.
And finally, for long welds, don't just weld end-to-end continuously. Break it up. Use smart sequences like backstep or skip welding to manage the heat and control the shrinkage.
Excellent summary. So we've just unpacked these essential fabrication techniques that really help keep welded structure straight, true to form, from those strategic tack welds
The stitches.
to the clever balancing act of back-to-back parts and that really intelligent choreography of the welding sequence itself.
And it's worth stressing, again, this isn't just about making things look nice and neat, although that's good too.
No, it's more fundamental.
Absolutely.
Yeah.
This is about ensuring the core structural integrity. It's about hitting the dimensional accuracy you need for things that have to be machined later or fit precisely with other parts.
And avoiding costly rework, or worse.
Exactly. Preventing expensive fixes, delays, or even in really critical applications, catastrophic failures down the road. It's about building things that work reliably, exactly as designed, straight out of the fabrication shop.
It really highlights how the art of welding is this intricate dance between immense force, all that heat, and incredible precision.
It really is.
And knowing these fabrication techniques that empowers welders, fabricators, engineers to not just stick metal together, but to genuinely sculpt it, to guide it into its intended form despite those powerful thermal forces.
Well said.
It really makes you think, doesn't it? What other maybe seemingly small how-to details or what other hidden forces are at play in complex processes that have these massive outsized impacts on the final result? Something to keep observing, keep questioning perhaps, keep learning how that mastery of the details really does shape the world around us.